So for this video, we're going to be covering section 5.1, and it's the introduction to what are called eigenvalues and eigenvectors. Now it's a little bit of a strange concept at first, and I'm going to start with an analogy that may not be the most accurate mathematically, but I think it really does get the right spirit for what we're trying to do here. So I want to start with the matrix A that is 1, 2, 2, 1. So this is our matrix A here. And what we want to do is we want to think about this matrix as a function. We talked about linear transformations before, right? So linear transformations were something that had, f of x plus y is f of x plus f of y. And f of constant times x is constant times f of x. So these are the things that you needed to be a linear transformation. And we mainly talked about the example where you have a function where to find the output, you're just multiplying by a matrix. And that's the example we want to use right here. So what I want us to think about is, okay, if my function is multiplied by this matrix 1, 2, 2, 1, then let's look at certain different input-output combinations. Let's suppose my x vector is in the x direction. Okay? Then if I plug it into the function, let's see if I can do some math here. I'm going to get 1, 2. And so what that means is my initial vector, my x, was directly right. And my new vector, my output, is in this direction. So I'm pushing it, I'm taking an input x and taking it to an output in a different direction. And I can do the same thing. What if my input is now the y direction or any other direction I feel like here? So okay, let's see what happens. Let's plug that in. And we should get 2, 1 here. So in this case, my my input starts out directly up here, and my output is going to be this. And so notice that you have one input, you have an output in a very different direction. So here's the analogy. Imagine that you have this really heavy box sitting on the ground, and you want to make the box move to the right, and you want to figure out how should I push it down there. Well, sure, you could push down in this way, right? You could be standing up and you could push down on the box like that, and it's going to move right. But because your input is down and to the right, you're going to be losing some of your force by pushing into the ground. Whereas the optimal way to push the box would be to push it, kneel down or whatever, to push straight on, and then all your energy that you're doing is going to push the box directly right, and you're not going to waste any of it. So this is the much better way to do it. And so what I want to do is I want to now apply this to our matrix here. What happens if the direction I start out in is the 1, 1 direction? So then I would go ahead and plug it in here, and I'd have 1, 2, 2, 1 times 1, 1. And what you're going to get is 3, 3. And notice that 3, 3 is the same as 3 times the initial direction. So that means my initial vector x is in the 1, 1 direction, and my output vector is in the exact same direction. And this is going to be the thing that we're going to focus on. We want to know when is the output pushing in the same direction as the input. And that's going to lead us to the following definition here. So here is the definition of an eigenvalue and an eigenvector. And you can't really define one without the other. You have to have both of them. So what it's going to be is whenever you have a matrix A and you multiply it times x, and you get something that is in the same direction. Now, in order to be the same direction, that means you have to be just a constant multiple of the original vector. Now, for whatever reason, mathematicians decided to use lambda as their multiple there. So whenever you have a times x equals lambda x, then x is an eigenvector, and lambda is the eigenvalue. So in our matrix before, where we had 1, 2, 2, 1, and we went ahead and multiplied a times the vector 1, 1, we got 3 times 1, 1. And so that means my eigenvector here is the direction 1, 1, and my eigenvalue is the number 3. So again, eigenvectors are always going to be vectors. Eigenvalues are always going to be numbers. And it turns out that this matrix has more than one eigenvalue. It's going to have 2 of them. And so let me just show you the other direction here. If I were to do 1, 2, 2, 1 times the direction 1, negative 1, I would get negative 1, positive 1, which is the same as negative 1 times the original direction. So in other words, a times 1, negative 1 is negative 1 times 1, negative 1. So that means my eigenvector would be the direction 1, negative 1, and my eigenvalue would be negative 1 here. So for this particular matrix A, the 2 special directions, the 2 best directions to push if you want to think about it, is not the x and y directions. It's the 1, 1 direction and the 1, negative 1 direction. So these are basically the 2 special directions. These are like the x and y axes here. These are the 2 special directions for this matrix. And it turns out each matrix is going to have some sort of special directions for it. Okay, so this is the idea of what it is, but 5.1 doesn't really tell you how to find these things. I kind of just told you to try them, and they worked. But when we go into 5.2 next, I'm going to show you the methods by which you can actually find these things that we're looking for. But the main idea is, I'm going to give you a matrix, and it will be a 2 by 2 matrix like this. And what I'm going to ask you to do is I'm going to ask you to find, first, both of the eigenvalues. And since I give you a 2 by 2 matrix, every one I give you will have 2 eigenvalues. And then once you have an eigenvalue, I want you to find the eigenvector for each one. So again, what we're going to be doing for chapter 6, your goal, is given a 2 by 2 matrix, I want you to first find the eigenvalues, and second, I want you to find eigenvectors. And again, I'm not showing you how to find these yet. That'll be in later videos. But I want you to really get down the idea that these matrices are going to have eigenvalues, and each eigenvalue is going to have its own eigenvector. If you tried to say that this would be the eigenvector for negative 1, that would be completely wrong. So each eigenvalue has its own eigenvectors that are different from each other. And that's an important point in this section. So the main idea of 5.1 is to understand these 2 terms and hopefully make sense of them. And then in 5.2 and 5.3, we're going to learn how to find these things. And then we're going to learn one use of them in 5.3. Why would we want to find them in the first place? Okay, so we'll stop at this video and pick up in 5.2.